MSI's Introduction to Apptainer, Containers for HPC tutorial slash workshop here. My name is Nick. I'm one of the scientific computing consultants here at MSI, which means I'm possibly one of the folks who you'll be in touch with if you have workflow questions, or you are interested in how do I get this piece of software up and running on MSI systems. Myself or one of my colleagues are likely to be pulled into that conversation on those tickets and email threads. And one of my areas of specialization is in deploying software for use on our cluster here. It's not as simple to install things on a shared user environment as it might be for installing it on your personal workstation. And some of those complexities motivate the use of different technologies for sort of smoothing over some of those rough edges. And Apptainer that we're going to be looking at today is one such technology for making it a little bit easier to get up and running with software in a shared user environment. So the first thing that I'm going to do here is drop into chat the link to the material that we're covering today. This will also be available on the tutorial webpage, either as a link to that site or as a PDF export. I'm not sure which is preferred right now, but one way or another, you'll have access to this afterwards. But if you'd like to follow along and look and be able to maybe copy and paste some examples, you can use that material as we go today from that location. Right. So let me queue up a couple of images here. We're going to want to talk through. And then yes, let's go ahead and get started with just a quick discussion, more specifically motivating and describing the type of technology that we're going to be looking at today in Apptainer. So we are, again, talking about installing software on the cluster, and there are a few ways that we can consider doing so. I have some images here, getting ready to share the screen. All right, there we go. A big cartoon blocky diagram there. Get this out of the way. Okay, so yeah, so before we get to describing, the type of system that Apptainer is, a container framework, and what that means, let us describe the limitations that we're looking to overcome that might make this useful for us. So when we're installing a piece of software, something that we actually want to use to perform our research, that could be something like MATLAB or something a little more domain specific, like a GROMACS or a SAM tools. And call that our target software, which here for our image examples will be software A, to be as generic as possible. To install a piece of software on a workstation or laptop that we own, this can still be tricky, but it is a little more straightforward compared to some of the other ways. So we start off, we physically have access to the hardware that we are working with, whether that's the workstation or the laptop, and we have control over swapping out components in that, or even now swapping to a different workstation that maybe meets our needs better. We're directly interacting with the hardware. Then that hardware has some operating system installed on it that we probably also have control over. We can install updates. If we are so motivated, we could install an alternate operating system. If your Windows workstation isn't doing what you want and you are interested in trying out one of the Linux distros, you could install Ubuntu or CentOS or what have you on this workstation that you control. So you have a lot of flexibility in terms of the platform that you are installing onto. And then there are going to be some, in the general case, some additional dependencies that you might need to install for a particular software. And these might come in the form of other executables that your target software wants to call, other programs that it expects to be present, or it might come in the form of other libraries that it needs access to in order to perform core functions internal to the software. And you can, because you have full control over your system, you can install these however and wherever you like. And then finally, all you need to do is point the install process for your target software at wherever you have installed the dependencies, run the install process, and then you are, in theory, off to the races and able to start working on the research that you want to do. Now, this looks very different in a lot of ways from the situation on a shared resource like the cluster at MSI. For a variety of security and stability reasons, we're not able to provide users anywhere near that level of control. We are a multi-user resource for thousands of simultaneous users, and so we can't have individual researchers coming in and interacting with the physical machines in the server room or tinkering around with the operating system on particular nodes. That just is not feasible at this scale. So the hardware and the operating system are essentially fully locked down. These are controlled by our systems administrators. And while you could, in theory, request that changes are made, we don't really have the ability to respond quickly or flexibly to those requests. And so this is sort of a static component that we're working with when we're considering installing software on MSI. And then the dependencies that are available in terms of these other executables or libraries that you may need to link to are going to be sysadmin influenced. We can install in our home directories some additional dependencies as we need to, but the process for doing that is going to look a little bit different compared to if we were doing this on the workstation that we control. And some of these dependencies will be installed as part of the operating system's package manager. So they will be installed to system directories and available in the system image, and you don't have to worry about loading a module or installing it locally. But this is, again, a little more inflexible because we can't freely choose where to put things. And then finally, at the top of all of this, we have our target software, which we do have to install in our home directory. We don't have access to system directories for installing anything. And we sort of have to negotiate, can the software that I want work with a partially flexible set of dependencies and a effectively fully inflexible set of operating system plus hardware? And there are ways to do that. In the workshop that I delivered, I believe it was 2 weeks ago, we go over a few different ways of installing software that works alongside this, including a quick intro to Apptainer, which we're going into more depth on today. And yes, so to make interacting with a system like this a little bit easier, because this requires specialized knowledge of sort of what is provided by the operating system, where the system components are, how do I engage with either utilizing or avoiding those components as needed for my particular workflow. Possible but complicated. There have been a variety of technologies that have been developed to, again, sort of smooth out and make more accessible sort of self-serve software. And I'm going to be talking today about one of these sort of abstracted software installation methods through containers. But this exists alongside another class of possibly familiar to you, depending on your background, abstracted installation methodologies through virtual machines. And in case folks have seen virtual machines, it is useful to maybe draw a distinction between how a VM sets things up and how Aptainer sets things up as a container engine to give us a sense of sort of what are we actually looking at and interacting with. So for our virtual machine, we're getting away from sort of having this weird rigid structure that we need to interact with, and we are making ourselves a little island where we can control all of the components that are north of the hardware. So the hardware is still fixed in this case. We still can't go down to the server room and fiddle with anything. But then on top of that, there is a component known as a hypervisor, which negotiates communication between these isolated virtual machines and the hardware. And each of these virtual machines has its own guest operating system. And then on top of that, you can install whatever dependencies you need and then whatever software packages. So in theory, this can be a nice way to encapsulate units of functionality for running particular research workflows. In practice, this requires a fairly substantial amount of expertise to get a virtual machine that is working for your needs up and running. And there are some security concerns with having a multi-user environment where you have a bunch of folks running virtual machines that are interacting with the hypervisor. There are ways to do it, but they're a little fiddly and they don't necessarily scale out well to being used by thousands of folks across the entire cluster. So we can think from a certain perspective of a container engine as being sort of a reduced scope way of making these little islands where we control things, where we still have our fixed hardware, still can't get down to the server room. And then there's an operating system that we are engaging with that underlies the container engine, which we are still not having any control over. And then on top of that, the container engine is running. In this case, this will be Aptainer for us. And this allows us to run these little independent islands that contain some set of dependencies and then the piece of software that we actually want to run on them. And this ends up being a little simpler to work with for the end user because you don't have to know anything necessarily about configuring your particular operating system to get a container up and running as you would for the VM case. Sorry, question in chat. Where is the kernel? Does the container access it? So yes, the container is running on top of the kernel. So the kernel here in our diagram would be somewhere inside our operating system. And each of these containers is needing to negotiate with that kernel through the container engine. It's excluded from this particular diagram. There's a lower level of detail. But yes, that is a constraint on containers if you are familiar with a higher level of detail for our system architecture here. Containers retain kernel info. So I'm not sure exactly what you're asking. Uh, could you give an example of the kind of information that you would be curious if a container had access to? Uh, for a different OS, different kernel, can the container run as expected? So sort of. So we can, on a Linux kernel, we can run a fairly wide variety of varied Linux distributions on top of that. Um, we cannot run Mac OS, we cannot run Windows in our containers if we're running them on top of a Linux kernel. Um, whereas that's a flexibility that's available to us in a virtual machine. And then another question, what is the importance of software A being the only option in containers and software A to C in VMs? That is a peculiarity of when I made these images. Could be software B and C and probably should be. I will make a note to update that figure. Yes, there's no meaning implied by the difference between um, A to C and only A there. All right. So I made a note to update that. But yes, I'm not attempting to imply here that we can only install a particular type of software in these containers. All right. Other questions about the uh, diagrams or the kinds of concepts we're talking about here? All right. Yeah, if nothing comes to mind now, feel free to continue posting those questions as they come up, and I will try to address them as we move through the rest of the material. Um, now, in terms of, I can stop sharing because the image is no longer directly relevant. And then I'll start sharing my terminal because we're about to use that. And we may as well just get the windows arranged. Okay, so for container solutions, so in that space where we want the isolation that one of these abstracted installation methods provides, but we don't necessarily want to fiddle with the full complexity of a VM. There are a variety of solutions that are sort of generally available to provide you with some way of running containers. And more recently have been coming out. I think the most famous one that folks are most likely to have heard of is Docker, which was originally developed for this meeting the same kind of need in enterprise infrastructure workloads. And it works well enough as a container technology for also running some containers on your personal workstation if you were so inclined. And so gained a lot of popularity for having the flexibility to test something locally, deploy it to the cloud, and with all the portability that comes with container solutions. But it doesn't work as well for us because of some security implications around how Docker containers are composed and expect to run. And so we're not going to be using Docker, although we will be able to engage with some Docker resources, as we'll see a little bit later. And so some of the other solutions in this space include Podman, Singularity, and Apptainer, which is the one that we're going to be using today. And Apptainer and Singularity are two Very closely related projects. Aptainer was forked from Singularity. Um, the last couple of years, don't have the particular date when that fork happened, but it's relatively recent. And they are relatively similar projects, and both intend to provide a container solution that works well in an HPC environment, HPC shared user environment, like the one that we provide. So it needs to be able to run fully in user space, can't require elevated permissions, need to preserve some user information inside the container so that we can sort of keep track of resource utilization and avoid some weird permissions exploits that can come from other frameworks. But the key things that we're going to be looking at here are that these, for either Singularity or Aptainer, but we're focusing on Aptainer, we have container images that are based on a single file in most cases. Other formats are supported, but we're mostly going to be looking at .cif files, which contain everything you need to run a container that has all the functionality that you built into your CIF image. And if everything is in that one file, it is easy to send that file to someone else. It's easy to archive that in some other storage location. Easy to share that out to someone else in your lab group. And the other key thing, aside from our security features, is that Singularity and Aptainer, and focusing on Aptainer, and I'm still working through the change in lingo, so I might slip up and say Singularity sometimes, but I'm intending to mean Aptainer. Allows us to integrate with some advanced resources that are available in our computing environment. In particular, it provides an easy way to pass in GPU resources for that kind of compute acceleration. And we'll look at some examples of how we can accomplish that a little bit later today. Right. So let's get to actually starting to use this. And I should probably get onto the cluster. All right, yeah, so I'm on the Agate login node right now. So if you're following along, you can start from a similar location in your terminal. And if we want to use Aptainer, the way to do so is we're going to module load Aptainer, because Aptainer is intended to be provided as a module at MSI. And then we have access to the Aptainer command. We can check the version of Aptainer is 1.3.6, which I think is close to the latest release. Should be fairly close because yesterday was maintenance. And we can also get the Aptainer help at this point, which allows us to see some hints at how we're going to be using this piece of software as we proceed. So one way that you can quickly get up and running with a workflow, if you have access to Aptainer, as we do here, is to grab an image that someone has already created that you know does what you need to do for your project. And there are a variety of libraries where you can look for these. We're going to start off by pulling from the Singularity container library today, where there are a variety of user-built images, but we'll also look at pulling from Docker resources and some NVIDIA resources later. We're not tied to any one particular source. So we can, if we need to, and believe that this is not currently necessary at MSI, but I'm going to include this for completeness in case you need to add a remote repository for another endpoint, or if you're using this, the information that we're presenting here today, if that's being used at some other center. So we can say apptainer remote add. We're going to say no login, because we're going to be accessing this anonymously. We're going to be accessing something that we're calling Scilab's Cloud, and this is at cloud.scicloud.io. And for me, and likely for you, you'll get an error saying that Scilab's Cloud is already a remote because, again, this is already included by default. And we can say then, if this was added freshly, apptainer remote use Scilab's Cloud, if we wanted to then set apptainer to pull by default from this new remote. And now we've set this as our default. And we can look at the list of remote repositories that we have available. We say apptainer remote list. And we can see that there are a couple listed here. We have the default remote, the apptainer cloud. Then we have the Scilab's Cloud, which we just tried to add a duplicate entry for and then switched to being the default. And then this is a local to MSI resource that we have for internal use. But now that we have a remote defined and selected as default, we can do things like try to find these image files to grab from that remote. And there's searching available in the command line interface here. So we could say apptainer search. If I want to find an image that is titled with Rocky Linux, can pass this query, and this can take a little while to return something, so we may not necessarily wait for it to do so today. And because this is not necessarily always the most responsive command line searching interface here, a recommended fallback is to go to the website for the particular remote repository that you're using and browse it through the web interface, because basically all of them provide a web interface that will be more responsive than this. But timed out well. And so we can see that there are 8 container images that are compatible with our local AMD 64 architecture that match our search string. For various different versions of Rocky Linux, as we can see in the description, and by various projects and developers, as we can see sort of in the URI here, where we're often looking at the name of the project or the developer as the first element after the library indicator. And then some information that gets more specific about what particular version of the image we're looking at. The default library provided ones here are the ones that are going to be blessed by the Scilab's Cloud developers. And so you can view these as maybe a default to safely interact with. And in my practice with my risk tolerance, I tend to avoid the images that are available from unrecognized users and projects, unless I have specific familiarity with that particular entry, because otherwise I don't have a lot of confidence in what I'm grabbing that it will be functional and safe to run. So for example, let's go ahead and pull one of our Rocky Linux defaults here. So if you want to grab, let's say this Rocky Linux 8.6, we can say apptainer pull. Then we give the URI after that, including the entire library designation. The library slash default slash Rocky Linux, if I can type. And then we provide a colon. And we can just say 8 here. The way these version specifiers are laid out, we can say either 8 or 8.6, separated by a comma. And those would pull from the same component here. And I have already downloaded this one. So I'm going to delete that so that I can actually do a fresh pull. So we'll see that behavior. So I had also had a cache version of that image available. If you are downloading this fresh and following along, you may have seen one or more progress bars that came up that indicated how close you were to completing the download. But then the end result should be that you have this this Rocky Linux 8.sif file, which is just 65 megabytes, which we have now pulled down, which contains all of the functionality that we were hoping to get from this particular entry, which we weren't searching for anything in particular here. This is just an example of how to pull, but this does contain all of the Rocky Linux stuff that you might need if this were your goal on a particular day. So let's also note here that this pull, one of the ways that we can interact with other types of container resources is to pull from a different location. So for instance, if we wanted to pull from Docker Hub, which is a large repository of Docker compatible images, apptainer will automatically translate those into a CIF file for us as part of the pull action. And all that we need to do is specify the different URI for the particular image that we're trying to get. So for instance, I happen to know that there is so this Docker / indicates we're pulling from Docker Hub. And I happen to know on Docker Hub there is a Rocky Linux image that I can download at version 9. And I've already got this one too. And get our cached CIF image. This can look a little bit different when you're pulling from Docker if you're following along. You're likely to get multiple download bars for different layers of the container, because that's how a lot of Docker images are composed, is this with these distinct layers that are composed on top of each other. Those all have to be independently grabbed and then composed into this single .cif file that apptainer is going to interact with. But that all happens in the background for us. All we have to do is say, all right, apptainer, pull from this different location. So now that we've grabbed these remote images, we can use them to perform Rocky Linux stuff. So let's use the Rocky Linux 8 image here as a way to get familiar with what happens when you run stuff using a container. So first, outside of the container, let us get a little more information about the system that we are running on for the host. So we're getting some more information about our agate login node right here. So if we list with our classifiers the root directory here, and this is just to get an idea of what is visible in our file system outside of the container versus inside, we see that we have some MSI custom stuff here in addition to the standard components that you would expect to find in the root directory of a Linux distro. So we have, boot, home, mount. Those are all things you might expect to see in any root directory here. But then we also have panfs, commons, scratch.global, um, projects, a few things that are particular to the cluster and how we coordinate sharing of storage space between users. And we can also, still outside of the container context, we can run ID to get a sense of what user we are here. So we have our UID for a particular username, and we have the GID for first our currently active group, which in this case is MSI staff for me. And then we have a list of all of the other groups that we might be a member of, and that's a lot for me. Hopefully less for you. I don't think there's a use case for a lot of users to be in every individual software group, but that's how I'm currently set up. And then we'll keep these things in mind and let us run these same commands internal to the container context. So one way to do that is we can say apptainer and then shell. And then we give the name of the .sif file that we want to run a shell inside. And so this is going to give us an interactive command line interface running inside the context of our Rocky Linux 8 that we just grabbed from the Scilabs cloud. And we can see that our shell prompt changes. It says that we are inside Singularity right now. Again, these projects very recently diverged, and so some of the tagging on these images still refers to the pre-fork project. But now that we're in here, we can run commands and get results based on the functionality inside the container. Now our container does still provide us with ls, so I can run ls and it's giving me information about my home directory, which I'm currently in. But let's rerun ls-f on our root directory here. And this is different than what we saw before. We are missing things like scratch.global and common and projects. There are some things that are still here, like mount and home are present in both locations. We have some new stuff here. This link to Singularity is new in this here. So question in the chat, is this from the OS or from the container? What we're looking at inside here right now is from the container. There is some information from the OS that is automatically passed inside the container. The command ls itself. So the command ls itself is provided by the container in this instance. Yes. Yes, we're running the containers ls and running it on the containers root directory, which has different contents rather. And if I run ID, I get some truncated information in important ways. So I still am the same user with the same active group, still the same UID, GID there. But I do not have additional groups beyond that one primary active group that I'm entering my container context with. So this is something to keep in mind. If you are a member of multiple research groups and you need to switch between them frequently, you will probably want to change the active group using the new group command before you start running things inside of your container context, because the container doesn't know anything about the rest of your active groups. It's an edge case workflow, but something that folks should be aware of because it can cause some confusion. If you expect a container to work and then you're accessing something in a different directory and permission denied, why is that? It's because you only have the one active group passed internal to the container context. And then we can get back out of here if we want to by either typing the exit command or hitting Control D. We're just exiting effectively a subshell here that's running internal to the container. I'll type exit because it's more visible on the screen. And now we are back into the host OS here. And all knowledge of my other groups is now visible again, as are the contents of the host file system. Now, an early question that you will often run into when trying to use a container for research is, okay, I can maybe grab an image file that has the functionality that I need, but the data that I wanted to interact with is stored somewhere that is not visible to the container. Like maybe I store it in scratch.global or in projects. So we can, if we want to, pass in paths from the host to make them visible inside of the container context. This is called binding. And there is an option that we use to pass those directories to the shell command called bind that will let us customize that a little bit. So we can say apptainer shell -- bind, and let's say I want to pass in scratch.global. And I want that to be visible inside the container. For the full syntax here, I want that to be visible at the same location, scratch.global. So our syntax here is -- bind, the location on the host, and then colon, the location that we want this to appear inside the container. These don't have to be the same. I could name this something else that was more convenient for my workflow. And if you are binding it to the same location, you do not need to have the colon and then the second argument. So what I have written here will work, but it is functionally the same as running bind scratch.global. Default behavior is to bind it at the same path. But for completeness of syntax here, because you might need to change your bind paths around, we'll include the full expression in our syntax here. And then finally, we provide, again, the CIF file that we want to run inside of. And we're again dropped into this shell. And then if we ls-f/, we see where we did not before have any visibility to scratch.global, we have global scratch. And I can even look at my own personal directory inside global scratch, which has some other components, some other CIF files that I've used in real workflows recently. And the same process can be used for binding in projects or other directories that may be relevant to your particular workflow. Then I believe we'll look at a couple of other ways to more flexibly bind things and some future examples, but just flagging that this is a thing that you may need to think about if you are operating on data that exists on the cluster. All right, so next I'll demo a couple of things at once. So we are able to, instead of running a shell as we have been, we could instead say, I want to just run a single command inside the container and then exit the container as soon as that command completes. And the command for that would be apptainer exec. And then we provide it a path to the CIF file that we want it to run in if we wanted to do an exactly analogous command here. But we can also, for either the shell or the newly introduced exec command, we can also pass it a URI. And as part of this command, the specified image will be pulled down to be used to run the command. So we can grab, for example, from Docker Hub, from the root project, we'll grab an image containing root. So this is the image that we're going to pull and use to run our example here. And then after this, we say the command that we want to execute. So we can say root dash B in this case. And this one, it looks like I did not have cached, so it is pulling down the individual layers of our container of our image file rather, from Docker. And it is composing a final image for us. Get some warning here because this conversion is not a fully solved problem. Sometimes errors arise, and sometimes you'll need to check out what may have happened during translation to figure out what the discrepancy is. But it will complete in a moment here for this example. And then once that is complete, inside the newly translated image, it will run that root-b. So finish the translation component. Now it's writing our CIF file. This will take just a moment. And then eventually, when it has completed, it will run root-b for us. Now we're seeing here in real time a potential drawback to if you do compose your commands like this. Say, in line, I want to grab from a remote location in one step and then use it to do something. You can potentially wait a long time, depending on the complexity and size of the image you're downloading, before this command will work. For our demonstration today, it wouldn't have made a difference. I would still need to download this image file either way. But if you're doing a research task that you're going to need to do repeatedly, then it's usually a good idea to instead do a separate apptainer pull to grab this image file to somewhere local, to some CIF file that you can refer to later, and then run apptainer exec on that CIF file as we had done with apptainer shell in the previous examples. Because otherwise, every single time you run, depending on the status of your cache, you might need to wait a not insignificant amount of time for the image to be rebuilt. This is taking somewhat longer than I had expected and longer than it has in previous demonstrations. So I'm not quite sure what the difference is today. Often, if you're waiting for a long time for whatever reason at your creating CIF file step, a common bottleneck for that is the speed of the storage that is being written to create that CIF file. So right now, because I'm not doing anything fancy, not even as fancy as changing directories to somewhere else, we're in my home directory. And so this CIF file is being written to my home directory, which exists on the network storage appliance that MSI uses to provide home directories. This is reasonably fast under most circumstances, but it's going to be definitely slower than if we were running this on a drive that was local to the machine, which I think we're going to need to switch to for further demos after this, if this is our performance today, because otherwise we will not be able to finish our material. So we might, yeah, instead of choosing to build in our home directory, choose to submit a job, request some temp space, which is provided by an SSD that is local to the node where the job is running. And then we might perform our image composition inside that /temp directory to have it run faster. The downside of that is that you need to copy the stuff that you do in temp back out of temp, because that everything in temp is deleted at the end of your job, whereas everything that's created in my home directory will persist until I remove it. But the need for a speed up here could certainly motivate us to change our strategy to needing to sort of manually save our data away from temp. Yeah, I think I will at this point. Oh, of course, as I'm getting ready to cancel it, it starts to work. Okay, just as I lose my patience. All right, so I did not terminate. I did not quite successfully terminate the process. And the CIF file creation finished, and we now ran the root-b command, which provides us with an interactive root shell that we can use to perform all of our root-related activities. Now, all that I want to do at this time with root is just quit out of this. So I'm going to use the .q command specific to root, drop out of this. And because we had run the aptainer exec command, we are dropped back onto the host operating system on our agate login 3 afterwards, because as soon as the root-b command completed, so too did our session inside of the container. And so this is run internal to the container, and then we're dropped back out as soon as it's done. All right. So I've been mentioning the image cache a couple of times. It's come up from when I've been re-downloading some of these demo images. And we'll just remind ourselves, if I rm the Rocky Linux 8.sif again, and then I say aptainer pull library / library / default / Rocky Linux : 8, and I have an extra colon in here. We don't need that. And it pulls it down, says using cached image. It did this for me last time. If you deleted and re-downloaded this image and you're following along, instead of seeing the download process, you should also now be seeing using cached image. So for convenience, aptainer, when we're doing these pulls, will store the image files in a hidden directory in your home directory, so that if you need to re-pull an image frequently, rather than having to download it, it can just say, oh, we've already got this locally on disk. We'll just copy it where you need it, and you're good to go. And it's a little bit more responsive than having to wait for downloads from remote servers and conversions from various formats. But this can potentially become quite a large use of disk space. And so it's something that we need to be aware of and engage with if we're going to be using aptainer frequently, because otherwise we might inadvertently run out of disk space, and that can cause all sorts of problems. So to see what is in our aptainer cache, we can run aptainer cache, a different subcommand, and then list, which is a subcommand of our cache subcommand. And this will give you a quick summary of what is present here. So I personally right now have 16 container files that are using almost 8 gigabytes, and then some blob files, which are those components that are associated with layers of Docker images. And I have way more of those, and they're taking up way more space in this case. And so the total space being used here is just shy of 31 gigabytes, which we only have, a relatively small allocation in our home directories, a couple hundred gigabytes, and so this is a substantial fraction of that and could grow to be a more substantial fraction of that if I'm frequently using Apptainer to pull novel workflows and not cleaning this up over time. So I can say Apptainer cache list -v if I want to get even more specific information about what is present, adding a level of verbosity here. Not completely helpful verbosity, as we'll see, but we get a table printed out where we have a generously named name of the container field, the date that it was created on disk, the size of it, and the type of thing that it is. Now, these names are a hash that is created from the image file itself. And so it's not clear at a glance without additional context what these exactly are, what they belong to. But we can see when they are created. I have some older ones from January, smaller and larger ones. These are all OCI blobs, so they are these layers of Docker images. And so we have a lot of them, and they can vary significantly in size depending on how much is present in that layer. Then we have this library file, which is, I believe in this case, the Rocky Linux image that we had just downloaded. And so this is a .cif file that is cached locally. And then we have some of these OCI temp, Singularity Hub, and ORAS type objects that are sort of the OCI temps are the outputs of converting the blobs into a Singularity compatible format. This S-Hub is similar to library, except we're pulling from Singularity Hub in this case. So this is another CIF file. These are all CIF files, just with different origins. And then these are also CIF files with an origin coming from that local to MSI registry. Things live as a different format on that server. And so that's what they are here. Now, if I wanted to clean this up because I'm running out of space and I'm saying, well, I'm not using most of these currently, and 30 gigabytes is a ridiculous amount of space for things that I'm not using in my local directory here. I can say apptainer cache clean and first run just -- help to see how we might use that. So you can provide cutoffs for removing cache entries that are older than a certain number of days. You can do a dry run mode to see what would be deleted if you're needing to delete some things and it's going to take a long time to re-download others. This is a sensitive operation. Using dry run first to see what's about to happen can be a good idea. If you're in the opposite situation, you're just like, get rid of all of it. I don't care as long as it's gone. You can use -f and it will suppress any confirmation prompts and just clean out everything that you specify. And then if you do need to filter, this $T for type allows you to say, I'd like to just get rid of all of my blob components, please, or just my S-Hub bits, or just my ORAS, or all. And I give a couple of examples of how this might work. So for instance, I could say cache clean -t blob, because I don't need all of those OCI blob things hanging around right now. And it's asking me if I want to confirm and say, like, if you're not sure what you want to do, use the dry run option. But I'll go ahead and say, let's go ahead and continue. And then if I run cache list, have no more of those blob files. They're using up the majority of the space. And so now I'm down to only consuming just shy of 8 GB here. And we could clear out the container files if I wanted to as well, but I'm going to keep those around because I'm still using some of them. But just as an example here. Now, it is also possible to be in a situation where you generate a large cache and you need everything in it because you're doing workflows that are quite varied in terms of the types of software they pull in, and maybe they pull down particularly large images. Examples might be things that work with a GPU acceleration and machine learning. Some of those images can be quite sizable independently. And so maybe you don't want to have to re-download all of those sizable files from slow remote sources, but you are running out of space locally. You can, if you want to, set in your bash RC file an environment variable called apptainer cache dir. And you can set this to a new location besides the default one. The default one is your home directory .apptainer/cache. But if you really need to keep your cache and need more space, you might say, all right, so this is going to go in some particular project here, and in my directory, and then a cache in there. And so you can set this to whatever you think is appropriate for your particular situation. I'm not going to set that. I'm happy with the default behavior, but just making folks aware of that this option is present at least. And conversely, it's possible that you are in a situation where you do not want to think about the cache at all. You don't want to use it. You just want to freshly download from wherever every time and not have to worry about space. Then there is a flag available to you for the commands that you run. You can say, for instance, apptainer pull. Let's say we wanted to re-download that Rocky Linux 8. We can say -- disable cache, and then we provide the URI. Linux :8. So if we say disable cache, it just ignores the existence of the cache overall. And so it will not download additional data into it, and it will not reference the cache to try and grab your container. I don't care to run that right now, but again, just flagging that this is available if that meets your workflow needs. All right, so that's sort of the preamble for using Apptainer for the most basic considerations of the most basic workflows that are possible with it. And that's still quite a lot of workflows. There are a lot of folks who make very functional images available that can be grabbed and used immediately to do work. So with what you've seen up to this point, you could, in theory, go and be very productive using those pre-baked containers such that they are available. But things get a lot more interesting, a lot more flexible, a lot more powerful when you start looking at how can I build my own containers? How can I customize the environment that I want to use to meet exactly my needs, and then share that out to other folks who I'm collaborating with so they're using exactly the same environment that I've put together. Now, at this point, and particularly because of how slow the construction of that CIF file for root was, I'm going to request a job allocation with some temp space, because when we are building these image files, the speed of the storage that we're running on will be heavily influential into how many examples we can actually look at in our remaining time today. So to do that, I like to use the salloc command, salloc, which will request an allocation for us that we can then SSH to that node and use the resources that exist there. This works similar to sbatch or srun in that we're going to provide some resource requests. So I want 6 hours of time for this. I only need a single node. Add tasks for node. I really only need a couple of processors for this. We'll see. We might have time for an MPI example, so I'll request 8. But if we were just building images, then I would only request probably 2. Then have this be on either AG small or AG large partition. Then another important resource component here is I need enough temp disk space, mounted at /temp to work in. 48 gigabytes will be plenty for us today. And then I'll also request 16 gigabytes of memory so that we don't run into constraints there as well. And this will take a moment to queue up and be allocated some resources. Now, if you haven't used salloc before, it does not immediately connect you to the resource that you have requested. It requests it, gives you some information about that process, and then says the node in this case, that you can connect to access these resources. So in my case, I have been given an allocation on ACN 16. So I can say SSH ACN 16 to connect to it. And now I have a session running with the dedicated resources that I requested. And then I will CD into temp so that I am working with the faster storage local to my current working directory here. And then we'll module load apptainer because we're again in a different shell session here on a new node. So for building containers and images from scratch, our end goal here is going to be to produce a .cif file because those have a lot of the benefits that we want from a container solution. They are more compact in terms of storage space used. They're immutable objects. Once they're built, you're not going to be going in and editing them. They are self-documenting. They say how they were built as part of the composition of the image, which makes them really nice for reproducibility and for distributing to other folks. But while we are sort of getting used to building our image files, and in general, when you are trying to build a new image file and it isn't working for some reason, you can build in what is known as a sandbox instead, where you can interactively perform operations on the image file that's going to exist as a directory, which is fully modifiable by you, both through the apptainer commands, and you can also go in and manually edit the contents if you would like. So good for sort of fooling around and troubleshooting when you're early in developing a workflow, but not great if you then want to take the result of your work and use it reproducibly or hand it up to folks. So let's create ourselves a sandbox to work in. To do this, we're going to use the apptainer build command. So we're going to be building our own image file, or image directory in this case. And to make it a sandbox, all I have to do is say -- sandbox for as a flag into build. Then I need to give it a name for the thing that I am building. So I'll call it my Ubuntu, which is going to be created in the temp directory here. And then I will pull this from Docker hub. We'll grab Ubuntu 20.04 because that is technically still supported until May. And so what this is going to do is it's going to pull down for us a local copy of the Ubuntu 20.04 and effectively unpack it for us into a directory named my Ubuntu. And this is a relatively quick operation. If we ls, we see that we now have a directory called my Ubuntu, which contains the kinds of things that you would expect inside of an image file, but it's just a directory right now. Now we can still interact with this via the apptainer commands. So for instance, I could start a shell using the my Ubuntu directory. It would be running inside a container created from that directory. So let's do that and add a couple of extra options that will allow us to modify the contents of this a little more cleanly. So we'll say apptainer shell, and then I want to change the contents of this potentially. So I'll say -- writable, which allows me to write the contents of this directory using the apptainer commands and inside the apptainer shell. And then I'm also going to say -- fake root, which gives us an approximation of the permissions that we need according to the Ubuntu environment inside of the container that will allow us to modify it according to the image files rules, not just apptainer's rules. And whether or not you need or are able to use the fake root command depends on the specific image file you're building from. Generally, fake root will work nicely with Ubuntu and other Debian-derived images, but there are other workarounds that can be needed for enterprise Linux family stuff and for minimal containers that are based on like Alpine Linux. But we'll stick with fake root for now for our Debian-derived Ubuntu. And then finally, we say the name of the image that we want to run a shell in with these parameters, in this case is my Ubuntu in the current directory. And it gives us some warning messages as we enter into the container here, but we now inside the container, we can run who am I? And inside the container, it thinks that we are root. We are faking being root. So that's the fake root, which will allow us to do things like say, I want to install some software inside of this Ubuntu environment. I can do that using the package manager, apt. So I can say apt update, and it will check what is available. And then I can say apt install, say build essential, and wget, because we are about to do a demonstration of building some software ourselves in here, and we're going to need to download some things in order to do that. So grab our compiler necessities here, and then wget for the downloading. And this proceeds just like it would as if you were installing this on an Ubuntu system that you had control over, except everything is being installed internal to our sandbox here. And we do not in general have access to package managers outside of container contexts in shared user environments, because those modify system directories, and we're allowed to modify the system directories of the apptainer image, but we're not allowed to modify them on the host. And question in the chat, someone rejoining us after having missed just a couple of minutes. So what we are doing, and I will paste a link that contains the commands, we have created ourselves a sandbox container that we're going to use to manually build some software inside of it. And this is not the recommended way of doing things for reproducibility, but it's nice if you are troubleshooting and also for introducing some of these components. And so right now we've just installed some software using the apt package manager, and we are getting ready to perform some additional steps. So in that link, I just
question.
yes.
Right. So For me, it's asking me if I want to continue since it'll need 64 megabytes of archives and then 273 megabytes of additional disk space will be used. Are we supposed to say yes to that?
Yes, you can go ahead and do
That's
that.
okay. You
Mhm.
think that's fine? Okay, thanks.
Yep. Yes. When you are building in in a sandbox component like this that's hosted in temp, I believe all of those files are stored locally to temp, so they're going against that 48 gigabytes that we requested. Um, and when we move to a more systematic build process later, using a definition file, we're actually going to modify our apt install commands to automatically accept that, and then it will be all those temporary files will be written to temp and then deleted prior to the finalization of the image. But in general, we are happy to accept those apt prompts. It's just sometimes useful to pause and see how much space is taken, and think about if we have enough space locally for it. But we requested that 48 gigabytes, so we should be okay with a few hundred megs. Excellent. All right. Um, so yes, we've installed our stuff with apt. So let's go ahead and set ourselves up to compile and install some software manually as well. So I'm going to do this in /opt, which is sort of a standard location for installing software in images. And as for optional software, is often additional software that is installed by the user. And by convention, this is where software is often installed in these container framework image files. So for convenience and politeness, we install to opt because that's where folks are going to look. And then we should often always look in opt if we want to know what's present in a container that has been manually installed. Uh, so that's the convention that we're using here. So we'll do that. We'll go to make a new directory in opt, which should exist by default. Opt exists by default. Our new directory will not. So we'll go ahead and make that directory, and then we'll cd into our new directory there. Clear so I have a little more space. Don't need to see all of the apt output on the screen. And then in here, I'm going to download the source code for a piece of software called Hammer, which gets used by some of our bioinformatics researchers, and is a quick thing to build from source, for example. So first we'll get our source code. So wget to download from the EdiLab. So http://edilab.org/software/hammer tar .gz. Grab the latest available release here. And it's a pretty quick download. And we are now left with our hammer.tar.gz present here. I will paste that wget command in the chat in case someone has a stray typo, and pasting it will just be easier. But failing that, once you have that download, we can now go ahead and extract this. So we can do tar dxf, then we give the name of the archive. So we're going to inflate this tar.gzip. And we now have this hammer-3.4 directory that contains our source code. And I'll perform a convenient step here that won't help us a great deal interactively, but it will help us when we are building this via a definition file script. So I'm going to create a standardized location for the source that I can always check for the hammer source at, rather than needing to know what the particular version is. Because if you'll see in our URL, we didn't specify a particular version to download. And so if this gets updated, we might get 3.4.1 or 3.5 in the future, and this path will change. And I can see and react to that right now, but that will not be the case in this group that we're going to be switching to in a moment. So we'll go ahead and create ourselves a symlink from hammer 3.4 to source. And then we can cd into source. And there's a GNU make configure make make install type workflow. So we can go ahead and run our configure. And what we're going to want to change is the prefix where this is installed to. Again, choosing to use the convention of installing something into opt here. So we'll say opt hammer install. Because we already have opt hammer / source, which is where we have our source code. Then we'll have opt hammer / install, which is where the functional software will be installed to. Go ahead and run our configure, and it will inspect our container environment and figure out how it can be made in here. No errors, so we can go ahead and run make. And this will take just a moment as it goes through and builds the software from source. And then when this is done, we'll run make install to have it finalize the build and install it into that prefix that we specified at the configure step. And this is all going substantially faster because we are running it in /temp rather than on the network storage available in our home directory. Still takes a moment though. There we go, just about done. Okay. So make has finished without any errors. Now we'll go ahead and make install. And then we can ls opt hammer. We see we have opt hammer install. We have our bin and share. And then inside of bin, we have all of our lovely, freshly created hammer executables. Now, we can, if we want to, now run these now. I can say, let's run nhammer. Just print the help for nhammer that we just built here, just to demonstrate that this newly constructed software does in fact work, and it works at least well enough to print itself a help menu here inside of our current shell. So build was a success. So we can go ahead and exit our shell session. And now we're left back on the host with our modified My Ubuntu sandbox that contains all of the stuff that we just installed. We can see ls My Ubuntu opt, we see the hammer directory, see install, we see bin. Now, we will not, in general, be able to just directly access the contents of our sandbox here and run them, because they were built inside the context of this Ubuntu environment, and they will work best and most predictably when they are run in the same environment in which they were built. So if we want to leverage the effort that we just used to run a command after exiting the session where we built this stuff, we can say apptainer exec, give it the name of the image, in this case, our sandbox directory, and then the name of the command that we want to use. we'll have to give the full path to the nhammer executable, and then we'll say -h again to reproduce what we just saw, except this time from outside of our image. And we get the same behavior again. So fantastic. We've created a functional sandbox here that performs at least some subset of the hammer functionality. We haven't tested all of it. But it does hammer stuff, and we could copy this somewhere else, and it would just keep doing hammer stuff wherever we copied it. We can also interact with this via shell. If we just want to run things inside of our container, we do not need to pass --writable or --fake root to it. If we just want to run things, we can just say apptainer shell my Ubuntu. And then if we're going to be working in the shell for a while, we could say, I don't really want to type the entire path to all of my hammer executables every time. So I can, for my own convenience, I can say export path equals current value of path, and then we will say opt hammer install bin, so that all of the executables inside this directory are visible to my shell here. Now I can say nhammer -h, and I don't have to type the entire path. And if I were doing a bunch of different hammer commands, this would be a bit of a time saver in terms of typing for me. Now, this still isn't ideal because that modification to the shell is not going to be saved when we exit the shell session and pop back in. So it's sort of an inconvenience that comes with using sandboxes. We can make that customization permanent alongside all of the other benefits that I've been discussing about having this encapsulated, immutable image file. If we change strategies from working in a sandbox to working using a definition file, which is the thing that we are going to be looking at next. Before we do that, what questions do folks have about the interactive build process that we have just seen? All right. Seeing and hearing none. I'll keep an eye out if I see any pop up in chat. I can address them. Otherwise, we will. Yes. So in chat, have a comment. It seems installing Ubuntu is wasteful for just one app. And I would say, yes, absolutely. Ubuntu is a very rich, complex, and large compared to other distributions option for building on top of. And there are many reasons that you might want to avoid doing so and prefer something like Alpine, which is designed to be as minimal as possible and therefore reduces complexity and reduces the size of the thing on disk. So if that's something that your workflows are sensitive to, then absolutely select a more minimal place to bootstrap from. The reason that Ubuntu is being used in this case and is used in a lot of cases in the production images that I put together is because the software that we are trying to deploy makes assumptions about where it thinks it's going to be installed. And a frequent assumption is that it is installed into a rich Linux environment like Ubuntu, often specifically Ubuntu. So it can be wasteful. You could create exactly a tailored environment for what you need, starting from a minimal starting point, again, with something like Alpine. But that is often more work than it's worth compared to just doing the thing the developers expect, which is installing into Ubuntu or CentOS or whatever they're targeting. But it's certainly not the only option, just the one that we're using here because of my experience. It's the most common approach that works. It's also not, doesn't result in a huge image file. And we'll look at the file size when we actually create a .cif. So I think it will take a second. Yeah. So without compression, in our sandbox here, we're using almost 500 megabytes of space for, again, deploying just this one app, which is certainly not optimal if space is a concern, and certainly not optimal if complexity is a concern. But again, works well for us in a lot of cases. All right. So let's move on to building ourselves a toolkit to work with definition files rather than with a sandbox here, because those will be a little more helpful for us for doing actual research tasks in general. So let us make first a simple hello world container, which will be even more wasteful because we're going to be using Ubuntu to echo hello world. So let's open up a file in your favorite text editor. Use VI. I'll call this hello world.def. And we will now write ourselves the most basic composition for a functional image file. So we need to start from somewhere to create our image. So we're going to bootstrap from an existing image. So we're bootstrapping from Docker Hub in this case, and we're again grabbing Ubuntu 20.04 in this case. And again, selection of specifics here, depending on your philosophy and use case, can vary, but we'll just stick with this for our examples here. This pair of lines takes the place of the URI on the command line. This is like docker ://ubuntu :20.04. The syntax just spreads that information out a little bit. Then we can specify what we want this resulting image file to do. So we'll provide a run script for default behavior, and we will have it echo hello world. And then we'll put in a comment. These definition files accept comments that start with the hashtag # octothorpe symbol, whatever name is meaningful to you depending on your age and context. We can say print hello world when the image is loaded, if we wanted to create an artificial comment that describes what's going on here. And we can, in general, have a few different sections that will look like here. We have our % and then the name of the block that defines particular properties and behavior of the resulting image file. And we'll look at more examples of those later, but here we're seeing % run script for what we want the container to do when we just run it. And this is all we're going to do for our hello world. In this case, we're just going to select something to start from and then select its run script behavior. We'll go ahead and exit. And then to build from this, we can say apptainer build hello world.cif. The build command expects what you are building as the first argument, and then it expects what you are building it from as the second. So we are building hello world.cif from hello world.def. And It's a relatively quick one because everything was already cached. So we've been working with that version of Ubuntu before, and we're not doing much with it aside from adding a run script internally. And now we have hello world.sif. And we can directly run this. You'll see it's got an asterisk here, which in my current shell settings indicates that this is executable. So I can just say / hello world.sif, and it will print hello world as the run script we defined. This is a shortcut for the also available method for interacting with this apptainer subcommand run. You can say apptainer run, and give the name of the image file, and it performs the same behavior. So we have a couple of ways of accessing the contents of run script, depending on what is more convenient for you. Then if we want to get rid of this or move it somewhere else or share it to someone, all we have to do is interact with our hello world.sif file. We can copy this to some other location if we want to save it, upload it to some server if we want to share it, or delete it if we want to get rid of it. This is just a file that contains our functionality. We probably also want to save our def file somewhere if we intend to maybe work with this in the future. So maybe we would copy this to some repository in our home directory that contains a set of definition files that we use, hopefully under some version control. These are text files that are amenable to it, so no reason not to. And just as a reminder, we're working in temp here, so everything that exists in here and is not copied out before the end of our job will be deleted. So just commenting again on, we have to actively choose the fate of these files under the current workflow. So let us create now a slightly more elaborate definition file to recreate the hammer sandbox that we had, but also add a little bit of convenience for ourselves. So let's go ahead and open up, calling it hammer in Ubuntu.dev. We're going to go ahead and open up this file. And I'm going to alternate between typing and pasting here. For things that we either have or haven't seen before. So we're bootstrapping from the same situation as we had before, Docker Hub in this particular Ubuntu image. Then we're going to introduce a new section to a def file, which is the post section. And the contents of the post section are commands that are executed inside the container at build time, which modify the base image. These commands are run only once when we run the apptainer build command, and they're never run again unless we rebuild the container after having modified this. So in this scenario, we're rebuilding hammer, so I can go ahead and just copy in the lines that I had previously used to build our hammer in the sandbox. Goodness, my copy paste is not working as expected right now. There we go. All right, and you do not need to indent in these sections, but I do so for readability and convenience. And there are a couple of changes to the sandbox workflow that we just went through that I will comment on. So sort of by convention introduced by Docker, because Docker works in layers and there is a layer generated per line, you will often see, if you're working with other people's def files, that related commands are both on a single line, and they're connected with double ampersand, so that both of the commands are run, and this is considered like one Docker layer. It's not meaningful in apptainer, but you will very frequently see this because a lot of folks are coming from a Docker background, and so it's just useful to be familiar with first, the syntax, and second, to expect that it will be present. And a slight modification to the apt install command that we had. We're still installing build essential and wget, but we're now passing this -y to the command, which will respond yes to that prompt that we hit earlier that says, this will take up so much space and download so many files. Do you want to continue, yes or no? When we run this, we are not going to be given the opportunity to interactively change the build. Everything is run automatically as a batch script, essentially. And so we need to say that you want to automatically reply yes to that prompt with -y. Then I am just combining the making and cding into of that opt hammer directory. We do familiar wget and inflation. Then here's where the symlink becomes potentially a little bit more friendly, where again we don't necessarily know what version of hammer we are getting, so we don't know necessarily what the name of this directory is going to be. We can create ourselves a standardized organization if we just link from whatever hammer version into source, then we cd into source, then we perform our configure, make install, just the same as we did externally. So that's basically the same as we had it before, with a couple of peculiarities because we're doing this in a script. Question here, how come apt doesn't require sudo when it usually does on MSI? So it sort of does require elevated permissions, quote unquote, inside the container. And that's where using the fake root came in when we were interacting with our sandbox. That pretends that we are root, which gets rid of the need for sudo. We're pretending that we are the administrative user inside of the container context. So that's how we're getting around that. It is the image files apt, so we're allowed to do things like that. Whereas we don't have those workarounds available on the bare metal cluster, so to speak. Then we can create another section for ourselves to build in a bit of convenience that was not available to us in the sandbox. So we'll do another %, then we'll say environment, and this will customize the shell environment that we are working with. So we can export path equals path opt hammer install bin. And so now I don't need to make this change every time I hop into a shell inside this image, and I also don't need to, if I'm just running an exec, I don't need to type this full path. I can simply say exec name of this image and hammer, which will save me some typing in the long run. We can still include a run script, which in this case might be nhammer-h. Question in the chat again, is the % environment just known by Docker or apt container to go into the shell like a flag? So I do not know specifically for Docker. I haven't worked with that in a while. I think it has something similar, but for apt container, what this is doing is it essentially runs this command when you enter a shell or when you exec a command which runs a subshell using the image file. So this is environment setup that is performed prior to any other commands being executed inside of the container context. All right. And then our run script here again will be what happens when we apptainer run, or if we run this as an executable, if we were so inclined, then we can provide some labels if we want. And say that this is authored by me, and that this is version 0.0.1 of this particular deployment. Then this information is available via apptainer inspect. And then we can also provide some help that is available. So this is an example container running the hammer help documentation. And this is available via another subcommand that is available to apptainer, which we'll look at afterwards. But this is now, a slightly more fully featured definition file where we're automatically installing some software, customizing our environment, defining default behavior, and then doing some labeling and documentation to be kind to our future selves. Best case, I would also include some actual examples of how to use the container to actually perform work here, some example commands. But we're not going to use this to perform work today, so we'll just have a little example text for our example container. And then I'm going to go ahead and write an exit, and then I can say apptainer build, and we'll make hammer in ubuntu.sif from hammer in ubuntu.def. And this will take just a little bit longer because it's needing to perform those installations from apt, and then it will also need to download, compile, and install hammer. But this is all being done in a scripted way. So just started the configure step for hammer. So the def file is a nice convenience because it allows us to access things like the environment heading, as well as adding things like the labels and help and run script. But it also is a thing that you could hand off to a colleague if you were so inclined. You say, well, the CIF file that I make for whatever my workflow is maybe too big to easily copy to the secure cluster that you happen to be working at, which has very restricted data ingest. But if you have a place where you can build an apptainer image file over there, I can give you the def file, and that will let you build exactly the same image that I built. And all you have to do is say apptainer build a new image file from this definition. So they can be convenient in that way. Wait just a moment for this to finalize. Now we have our hammer in ubuntu.sif. I can run that to get my help here. Apptainer exec, hammer in ubuntu.sif, -h. So functionality is all still there. The file size, I believe, is smaller because there is some compression that is applied. So rather than the 500-ish megabytes that we were for this, it's been compressed down to 191, which is still pretty big for a single application. But it is slightly smaller just because of the way the file format works. Now, if we want to take advantage of some of that additional tagging we provided, we can say apptainer run -help. I can type hammer in ubuntu.sif, and it prints out the help that I had written inside of my help section. I can say apptainer inspect hammer in ubuntu .sif, and this will provide some of the information that I tagged along with some automated tagging that is done when the image is created. And I don't do a lot of it apptainer inspect, but if we check the help here, we can see that there are some options to expose some additional components here. Like I could get the def file back that's stored internal to the image, or I could look at the environment. I could say apptainer inspect -d and we're in Ubuntu.sif, and we can see that the image file here stores the entire def file internally, which is handy if I need to reproduce this. And I have the functional software, but I happen to lose the def file somehow. It contains the instructions for how to build another one, which is nice. If I need to tweak and modify in the future, this can be quite useful. And just for completeness, if we change this to -e, we can see the one little modification that we made to our environment coming at the end of how the path is set up by default inside of this particular Ubuntu image for some of these system paths. And then again, to emphasize the fact that we're working in temp here, I will cp hammer in ubuntu.sif saying, well, I actually want to keep this. I like how this turned out. I'll copy this into my home directory, and I'm also going to cp hammer in ubuntu.def into my home directory. And so now they won't be lost when I exit the job and everything in temp is deleted. Just a couple of quick notes for best practices for building containers. So if we cat .def, we can use this as an example to talk through. So the first one, I mentioned before that we should prefer installing things into opt if we are selecting directories for them. This is for that convenience convention that I mentioned. Everyone thinks to look here, so install here. If you need to install somewhere else for some reason, you should definitely avoid installing into locations that are likely to be overridden by binds. So like if you know that you're going to be needing to get data from somewhere in /projects or somewhere in /.global, do not use a directory /projects or /scratch.global internal to your container to install the software, because when you bind those external directories in using that bind option, the external components will overlay the internal components and your installed software will not be available. I'm sure there are workflows where that would be useful, so I'm mentioning that it's a consideration here, but in general, don't install things that are required bits of functionality for your container into places that are likely to be overlaid by the external file system. And then don't include secrets inside of your either your def files or your images. Things like SSH keys or cookies that authenticate you automatically to different locations, or things that are security components like that, because there is nothing in the construction of our def file or our CIF file that obscures those in any way, and so you are essentially, when you bake them into either your definition or your image file, just giving them away to whoever has access to those in the future. So avoid building in secrets for that reason. And I will also mention that it is possible for us to build a sandbox container like we did here, and then convert it from a sandbox into a single image file. And that would do some of the compression for us. that is occasionally useful, but in research, it's usually not the right thing to do. Usually, what you want to do is instead to start from a def file, because the CIF file that you get from a sandbox will not contain any information about the way that it was built and modified, and so you're creating kind of a black box container that is difficult to work with if you need to update or modify it in the future. So better to keep our recipes exposed in these def files where possible. So question in chat, in theory, you can put all your commands in def, but if there is an output, like a CSV file, is that put into the container and can be accessed from a collaborator? So not quite sure the workflow that you're imagining here. You, in our def file, so we're not doing any like productive research task in here. We are setting up the environment that we're going to use to perform a research task. We would almost never, I only use almost because I'm sure there's a place where this would be useful to someone. We would almost never in our post section then include like, okay, now let's actually run opt hammer install bin and hammer on some data, and then it outputs some output. Like we would basically never do this unless this output was something that would always be needed as input for further workflows with this particular image file. So if this is similar to the case you're thinking about, and the CSV that you are generating is important input to all future steps that are going to be run with this image, you could bake that into a standardized location and maybe make an environment variable that points to it if that's convenient for you. But more frequently, you will not have something like this in here, and you'll simply have set up your environment. And if you wanted to, produce the output, you'd say, apptainer exec hammer in ubuntu.sif, and then we would run our command on some input and then create some output. And this command is being run internal to the container. And depending on the path you specify, it's going to be saved somewhere external to the container. But the output here is not associated with the container, except that the container was used to generate it. So, okay, good, 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 good. Yeah, there are a few cases where I bundle in some data with a container, usually to support test cases. So you can certainly intentionally include data in there, but I think it's more common to include less data and rather have the data be interacted with external to the image. Although I don't work with every workflow, so there are certainly exceptions. Other questions about building here before we go in a little bit deeper on binding behavior for these internal versus external directories? All right, so we'll go ahead and look a little bit deeper at the behavior of what is visible inside the container in terms of directories from the host. So we had already seen the behavior of slash or rather dash dash bind shell or exec dash dash bind, and then we said scratch dot global, um, and then we could say hammer ubuntu.sif, and then we have scratch dot global. Don't need to list everyone's directories. We just list the root and see that scratch dot global is present inside of our container here. But there's a little more subtlety to what's going on. There are some things that are included by default that we can choose to exclude if it is convenient. And so, for instance, as currently configured at MSI, the user's home directory is automatically included inside of the container context. And that will be whatever is defined via the home variable. So by default, users3 done 0404 is going to be visible inside any of the containers that I run. The PWD, whatever the current working directory is also going to be included whenever you run the apptainer command for your convenience. And then there are some system defined paths that are passed in by default because they are usually useful to do so. Things like /temp, /proc, and /dev are passed in by default unless you tell them not to. Now, if you are in a case where things are a little more sensitive to whether or not those particular directories are visible inside of the container and you don't want them to be, we can say, for instance, some pseudocode. We could say apptainer run dash dash no mount no mount, and then we need to say what we don't mount. We no mount space temp, and then my container.zip. So we would exclude mounting /temp into something with the name my container here. We could also say that we don't want to mount home, or we don't want to mount proc. And there are lists in the apptainer documentation of how the different directories are referred to by these no mount strings. We're not going to enumerate them here, but that is available in the apptainer documentation website. I think it's in association with the shell command where it's linked. But if you look up the no mount flag, that should be relatively straightforward to find. And I guess just for completeness, if for some reason you want to bind nothing inside of your container, so we could say container shell dash dash no mount. And if you say bind paths, it will just give you nothing from the host inside of the container, if that's what you need for your particular workflow. Make you aware that it's available. Now, we had already seen if we want to bind in a directory with the dash dash bind. So let's use a particular example to sort of play around with that behavior a little bit more to make it more explicit. I don't remember if I deleted this from last time, so we'll see. So we'll try to make home my data. Looks like I already have it. So ls. All right, so inside this directory, I have a text file which contains a mass of a muon, which maybe is useful for the research that I'm about to perform, and I want this information passed in as data to the particular container that I am running. And if it's very, very important, then maybe I'm referencing this text file frequently in my workflows. And so I want to have this available at a convenient location. So I could say apptainer shell dash dash bind home my data. And then rather than binding it to home my data, remember home is included by default, so this would already be accessible, and I'm just making things more convenient. I could bind this to a location inside the container called /data instead, and so I only ever have to type /data in the internal commands. I don't want to think about what kind of workflow would require a bioinformatics tool and a massive muon, but we're going to pretend that we're doing one of those right now. And if we ls / we see that there is a data, and I can cat data muon mass, and this information is available at this more convenient path inside of the container. Go ahead and exit there. Now it's also going to be a fairly common workflow for most folks that they might want to bind several extra directories. And there are a couple of ways to do that. One of them is by modifying the syntax of our bind here. So we can say apptainer shell dash dash bind, and then we'll keep home my data being bound to data. And then we'll have a comma to introduce another bind that I want to introduce. We'll now bind, oops, / scratch dot global, and then we'll choose to not sure if you see it, but on my screen there's an annotate button that is hiding my text. So scratch.global / scratch. So we're binding this to a different location. And then we'll hammer in ubuntu.sif. And we could include further commas and further pairings. Now, if we ls / we have a scratch inside of our container that contains, again, that global scratch contents, just at a different path. And we could extend this as long as we need to include as many of these various paths into our container as we like. So that's one way. If you're familiar with Docker, you can use the -- mount flag from Docker. You can only use bind mounts with that, so there's not really a reason to do it that way unless you're just like really comfortable with that syntax. I'm not going to do the example here, just call out that if you're coming from a Docker background, mount is available for your convenience as well. And then perhaps a nicer convenience is that if we have a lot of paths that we want to bind to every container that we run, we can set an environment variable that will be interpreted by our apptainer commands and will modify what is bound wherever that variable is set. So we'll export apptainer bind, and if we just make that scratch global, now if I do apptainer shell hammer in ubuntu.sif without doing any special bind modification of my command, I have scratch.global present in here by default. And so I can set this in my bash RC if I know I'm always doing the same thing every time to have this conveniently set up for me without having to fiddle with it each and every time I log in. The syntax here is similar to the use of additional binds on the -- bind command. If I want to bind this to scratch instead, I can use a colon and change the target of it. And then I can say comma. I want to also bind in my data to data as I did before. Then I can do that very similar syntax to what we used on the command line. And then we have now data with our muon mass. We have scratch by the change name. Important question. What is the purpose of bind? It is binding and not copying files. So workflow that you're running would not translate to a peer's machine. Is there a purpose that you're missing? Yes. So we are not, when we are creating a container, able to anticipate all possible input data that someone might ever want to use with the particular research functionality that we are bottling up for future use. You can think about this as like installing a piece of software to a computer. When you install the software, you do not attempt to install all possible inputs that would ever be used in the future alongside it. You allow the user to provide those at runtime. Perhaps you provide some data at install time, and because it's frequently used, and we could also include some data inside of our image files if it is frequently used and would be useful to everyone running it. But the binding is how we are sort of customizing the locations that are visible on our machine to include unanticipated inputs, where we build in all the tools to run a molecular dynamics simulation using GROMACS, but we don't know what system someone else is going to want to simulate. And we allow them to provide their own structure files and own force fields and such to perform a custom simulation using the same fixed piece of software. And so we might include those input files through binding to make them visible to the container, because we can't anticipate them at build time, but we need to make them visible at runtime. Okay. Yeah, it's a subtle difference, but a key one. So thank you for clarifying that. Do folks have other questions before we move on to a couple of more HPC focused sections? All right. Seeing none, we'll go ahead and proceed. So we've looked at ways to build and interact with these Aptainer images. But at MSI, you are very likely to want to run jobs using Slurm that use your Aptainer images. You're not likely to be always performing your work interactively on the command line as we have been. So if we wanted to create a batch script that would, for instance, Aptainer exec, and if you remember, we copied my final hammer in ubuntu.sif into my home directory. So we're going to reference it at that location because it was copied over there. And then we say the productive thing I want to do for my job is once again print the nhammer help. So we can run an image file from a location and have it run a command. We know those tools. And it is a direct translation into a batch script from this to the standard way that you might compose a batch script. So if I create an example slurm script .sh. I'll just go ahead and attempt to paste this in if pasting is working for me here. So similar to any other Slurm batch script, we start off with our shebang for what shell we want to have interpret it. Then we have some sbatch directives that specify the resources we are requesting for the particular job. We module load apptainer so that apptainer is available to run our actual command that we want to perform in this very serious and useful job, where we run apptainer exec on that stored image file to again print the nhammer help. So nothing fancy here. This just slots in sort of as you would expect for the commands we have been interacting with. And then you would say sbatch example slurm.sh and you'd submit it and it would be run when the requested resources were available. So that's maybe not especially interesting. But what if you want to do something a little fancier? Like what if you want to have your container interact with a GPU? Want to use that to accelerate a particular calculation. So let's go ahead and first grab ourselves an image that provides some GPU acceleration. So we'll apptainer pull Docker nvcr.io. This is an NVIDIA provided service from their HPC line of images. Then we're going to grab GROMACS, the molecular dynamics tool we've been talking about. We'll grab, because it should just work, the 2023.2. Now, we are grabbing an NVIDIA provided image file here. Because NVIDIA makes GPUs, and they also expend a lot of engineering effort on building software and distributing it in ways that can utilize the GPUs that they construct. And so they have this lovely nvcr.io, which provides a bunch of software that is sort of ready to go as long as you know how to point the resulting image file at a GPU on your system. And then you can just sort of immediately use it for GPU acceleration. Go ahead and download this. Take just a moment to, because it does have to convert this from the Docker format. I'm going to make a note, so I've noticed a need for an update in my apptainer thing. Update the name of a partition in one of my example scripts. And we'll see that in a second. So I'm going to go ahead and then CP that GROMACS out of temp into my home directory. Because a new job is not going to have access to /temp in the current job. So just downloading it here doesn't do us any good, aside from making it faster to build in the first place. And we can just copy it over after it's built. Then if I want to have a molecular dynamic simulation that will utilize this image for GPU acceleration, I can craft a slightly changed job script that will do that. Call this creatively GPU example.sh. And I'm going to copy in errors in two places. So I'll need to modify what I copy in here. So to change the partition for my example, if you're working from the website, I have an old name for a specific GPU partition on there. You should instead use MSI GPU at this point. Um, so we have the similar resources that we had requested previously. These might change for a particular calculation that you're doing that might be more or less intensive on a particular resource. But we need to request the MSI GPU partition in order to have access to GPU hardware. Then we have to request the general resource of a GPU, specifically an A100 GPU, and I just need one of them for this. And then it's, again, very similar to what we had before. We module load Apptainer. We will intersect another error. Apologies. So we Apptainer exec, then we say dash dash NV, which stands for NVIDIA, which means we're passing in information about NVIDIA GPUs that are available on this host into a container based on this GROMACS image file. And then inside of that, we're going to, in this example, not run a calculation, but we're going to interact with the MD-run executable to print its help menu again. But if we had an input file for a simulation, we would include that here with the appropriate flags, and then this command would allow us to actually perform a GPU accelerated GROMACS calculation. The key changes were just running this job somewhere that has access to a GPU, and then including this dash dash NV flag. For some of these containers that NVIDIA provides, some of the older ones in particular, like 2021 and earlier, they can occasionally be a little bit finicky with picking up specific GPUs from the host, even when you provide this. In those cases, you might need to include an environment variable, Apptainer CUDA, visible devices equals, and in this case, we only have one GPU, and they're indexed starting at 0. So this is just reinforcing to Apptainer that we want to make the first GPU CUDA device visible inside of our container. If you had 2 GPUs, you could comma separate and say I want 0 and 1 in there, and so on if you need additional ones. This is usually not necessary, but I wanted to flag it as a common problem solving step if you are trying to do this and the sort of straightforward way isn't working. Try forcing these devices to be visible. About half an hour left, which is not quite enough time for all of the remaining topics. So I think, so the 2 remaining topics that we have to cover are running MPI parallel codes with Apptainer. I'm working through an example for that. And then running instances using Apptainer. So you would have a defined image file and you would set it up to run a process in the background. You could think of this like a containerized web server sort of thing. Um, and both of these are potentially quite useful. But we don't have time for both. So I think what I will do, the MPI one is a substantially longer example, and we might not have time for it independently. I will just briefly comment um, that we need to, so I'll link the specific chapter into chat here that goes through that example. Um, and then I'll go with sort of the take home from this. If you are familiar with running MPI codes, you you will perform the same familiar steps to build your MPI software inside the container using MPI compilers that are inside the container. Um, but when it comes to runtime, you are going to want to use MPI outside of the container. So what this ends up looking like is rather than saying apptainer exec MPI run dash np2 example, I will say this is MPI example.sif for our image file, and then we want to run this MPI command. You would not do it like this, because this would use the MPI run that is internal to the container. Now this will do something, but it's not usually going to be what you want to do at MSI. Now what you are more likely to want to do is instead say, I want to run example that was built inside of my image using the MPI compilers and libraries that are built inside of there. But I will say MPI run dash np2 outside of apptainer. So MPI is going to be instantiating two instances of this apptainer exec and coordinating effort between them. And this ends up being the better situation for the majority of cases that you're going to be wanting to run MPI at MSI using containers. There's some more detail about it on that page that I linked, but I just wanted to sort of flag the biggest sort of caveat for interacting with this type of workflow. This also means that you'll want to select a version of MPI to build with inside of your container that is also available outside of your container. So if these versions are the same, then things will work without much friction. If they are different, then best of luck. Sometimes things work, sometimes they don't. So a few extra things to take care of if you want to use MPI for parallelization with these image files. But yeah, so then let's move on and take a look at instances, because that's a little more special to apptainer. So let's go ahead and we'll pull down a new version of Rocky Linux 8 into our temporary directory here. Oh, and I get to build it for the first time. This is the first time it's not being built directly from cache. All right, and so I have my Rocky Linux 8.sif file here. And now let's say that I know that when I run this, it does something interesting, and we'll look at more illustrative examples in a moment, but we'll look at first just the basic syntax for starting an instance. And we'll say apptainer instance start Rocky Linux 8.sif. And then we also need to provide the name for this instance. We'll call this my Rocky 8. And then we get this information that instance was started successfully, and we are dropped back into a shell that is in the host context. If I run apptainer instance list, you can see that there is a currently running process. It has a process ID named myrocky8 that is running off of this CIF file. Now, it's not doing anything especially interesting because we didn't select or set up a web server or something that does something in the background, but this is sitting here waiting for input, just sort of idling, waiting for us to interact with it. The only way that we can really interact with this is to enter a shell, or you can exec with it as well, but we can say apptainer shell instance : my Rocky 8. And now we are running a shell inside of this continuous instance, which might be useful under certain circumstances if you need to have like a couple environments that take a while to spin up running in the background. You could sort of toggle between them using apptainer shell. And then when you're done with them, you can say instance stop my Rocky 8, and then apptainer list shows that we don't have anything currently running. So that's the basic syntax, but nothing fun happened there. So we could, if we were so inclined. And for this, I'm going to grab an open on-demand session, and we'll work within that environment. Because what I want to do is set up a little toy web server and then open up a web browser and demonstrate that we can interact with that local to the node where that instance is running. So we'll go ahead and start that queuing. That'll just take a moment to start. So it's already starting. Good. I'm going to share a new window, which will be a terminal session in this new instance. Or not we're using instance as a different thing for apptainer in this new job, so that we have the ability to open up a web browser and navigate into the web server that we are going to set up. And hopefully that will launch eventually. But let's go ahead and cd into temp here. And this is a different job, so it has a different temp, has none of the stuff that we were just working with. But we can create ourselves a basic index.html file. So we'll go ahead. I don't want to paste, don't want to work with a bunch of typed HTML. So we'll go ahead and just paste that in. So we are basically doing a very simple HTML document here that has a descriptive title, friendly heading, and then some text in the body of the document. And I'm going to create a web server that will display this in a way that we can access via a web browser. So for this, we'll go ahead and make ourselves a new def file. Because we'll need a purpose-built image that has the web server bits we need. So we'll go ahead and create basic server def for this. And we can go ahead and type it. So we can bootstrap Docker. This is another very wasteful thing. We certainly do not need Ubuntu to serve a simple HTML document. We'll make ourselves a post section where we get updates, install -y Python 3.9, and we're going to be using Python's http.server for this, just for a simple way to get access to this. We'll also introduce a new section here. If you need to stage some files that exist on the host into your into the final image that you carry around. So this would be a way to sort of bake in data that is always going to be required. The files section, and we're going to say, I want you to copy at build time what we have in index.html. And I want this to be copied into temp index.html, and this will be the location inside the container. And I believe we're doing that for convenience with respect to the particular Python that we're using. In this case, that happens to be the same location because we're working out of temp for speed, but there will be this overlaid index.html that is available every time we run this image. Then if we give ourselves a start script, this is something that is new to instances. This will say what the image is going to do when we start it as an instance. So this is distinct from run script. This will only happen when we create a new instance. So we'll cd into temp, and then we will run Python 3.9. We'll use HTTP server on port 8850. So just a little bit of a couple of commands to set ourselves up to actually serve our index.html. Go ahead and WQ on that. If we build basic server.sif from basic server.def, and take just a moment to build. It's not especially complex or heavy. So wait just a moment for this to create the SIF file. All right, and then we can say that container instance start. And then here's an instance where here's a case where no mount is going to give us more predictable behavior. We don't want to mount our external temp because we want the internal temp where we are staging the index.html to always be present. So we're saying don't override that. Always just use the one that's internal to the image. And we're going to run basic server.sif as my web service. Enter instance list, so this is happily running. Then we'll see if I can run a web browser here. Hey, Firefox, there we go. Chrome fails me, but Firefox works. So we can HTTP :localhost:8850. And now we are in a separate application interacting with the very basic web server that we have running on this port. Now, this is not, I will say, the most interesting application of this, because importantly, this web server is not available outside of this node. So I'm not serving this out to the wider internet. I'm just making a web app application available to me local to this particular job. Now this gets a little more useful in cases where you have a piece of research software that runs via a web server that you want to make available to you using the resources inside of a job. An example might be a Jupyter notebook. I do have a worked example that is available like directly to that chapter as well for a Jupyter notebook, but we do not have time remaining to do that demo. It takes a little bit longer to build, unfortunately, but the principle is the same. You create an image that has a web application and its dependencies installed, in this case, Jupyter. And then you provide a start script that allows the image to know what to do when you start it as an instance, which would be to run a Jupyter notebook on a particular port. Build the image, start the instance, and then you could interact with your own sort of custom-built Jupyter notebook here. And it's not just Jupyter Notebook. There are all sorts of other applications that are intended to be run as sort of a web application and then make use of the browser for rendering their graphics. And the same basic workflow would apply in those cases. Install the software, provide a way to start the service in terms of commands that it requires when the instance starts, and then build and start the instance as we have seen here. So it's another sort of niche case. Just like not everyone is going to be using MPI or a GPU, not everyone is going to want to use a web server instance with these things, with images, that is. But it is useful to know that it is available as a tool in your toolbox if you have Aptainer available to you.